Predicting climate model simulation crashes. This lesson will help you tackle a real-world classification problem using data from climate model simulations. When scientists run climate models, sometimes the simulation crashes due to unstable parameters. You will learn how to use Python data tools to predict which simulations will fail, which is very important for saving time and resources in climate modeling. Step by step, you will explore the data, visualize key patterns, avoid common errors, and build a useful predictive model. By the end, you will run an end-to-end workflow, from raw data to model evaluation and results. Running the cell now. We import NumPy for fast number crunching. We import pandas to load and analyze tabular datasets. We import matplotlib for plotting and visualization. We import Seaborn for prettier statistical charts. We import train_test_split from scikit-learn to split training and test data. We import random forest classifier, a robust classification model. We import reporting and evaluation tools for classification tasks. We import standard scaler to normalize numeric features. We import PCA for dimensionality reduction and visualization. We import warnings to control warning messages. We filter out warnings to keep output clean. Running the cell now. Practice. Can you think of why reproducibility matters in scientific code? Data concepts for climate simulation crashes. The dataset tracks simulation runs from a climate model. Each row represents a unique simulation, described by 18 numeric parameters. The outcome column is the target, 1, crash, or 0, no crash. Predicting crashes saves computation, energy, and time. Common beginner mistakes include ignoring class imbalance, assuming all features are equally important, and forgetting to check for missing data. Running the cell now. First, let us fetch the climate model data directly from OpenML. We fetch the dataset from OpenML using scikit-learn's fetch_openml tool. Importing fetch_openml from scikit-learn.datasets to load datasets. Setting the C to 42 means our results are always reproducible. We extract the actual data as a pandas data frame from the OpenML dataset. Creating a copy of the data frame to avoid modifying the original data. Printing a message to indicate that we will show the first 5 rows of data. Displaying the first 5 rows of the data frame to inspect the data. Running the cell now. Here we load and display the first 5 rows of the climate simulation dataset, showing 18 numeric parameters per simulation. Notice the range and scale of these continuous features, which will be important for downstream pre-processing and modeling. This step confirms the data structure and helps spot any immediate issues before tackling crash prediction. Which features look numeric or categorical to you? Let us explore the shape, types, and balance in our dataset. We display the shape of the data. Shape tells us number of rows and columns. Then, we print out the column names to see what features are available. We show the data types for each feature. This helps you quickly check for numbers, dates, or categories. We show the data types for each column to understand what kind of data each contains. We check how many examples are in each class. Class imbalance is very common and important to notice early. Finally, we show the fraction of each outcome value in the dataset. Running the cell now. This output shows the dataset has 540 simulations with 19 columns, including 18 numeric features and the categorical target outcome. Notice the severe class imbalance, with crashes, class 1, making up about 91% of cases, which is crucial to address when building predictive models to avoid bias. Understanding the shape, feature types, and imbalance helps ensure appropriate pre-processing and model evaluation strategies in later steps. Why does class imbalance matter? Try explaining it in your own words. We will confirm there are no missing values, based on the dataset documentation. We check for missing values by summing all missing entries in the data frame. This helps us avoid errors down the line. Since the dataset has no missing values, we expect to see 0 here. Running the cell now. This output shows that there are 0 missing values in the dataset, meaning every simulation run has complete information across all 18 parameters and the outcome column. This is important because it allows us to proceed without data imputation and ensures that missing data won't skew our crash prediction model. Checking for missing values early helps avoid a common beginner mistake in data preparation. Practice: what would you do if there were missing values in the data? Let us make a simple bar plot to show how many crash versus no crash events we have. We use Seaborn's count plot to plot the distribution of class labels. This makes class imbalance immediately obvious in the target outcome. We add a title for clarity. The plot displays the results. Running the cell now. The bar plot shows the distribution of the outcome variable, revealing a clear class imbalance with many more simulations that did not crash 0 than those that did 1. Noticing this imbalance is crucial because it influences model training and the evaluation strategy, ensuring we don't develop biased predictors that overlook rare but important crash cases. This step highlights the importance of understanding your target variable before building any predictive models. What does this class imbalance suggest for our prediction strategy? Now let us use describe to see summary stats for all features. Describe gives us count, mean, minute, max, and quartiles for every feature in the data frame. This helps you spot any weird ranges or outlier values immediately. Running the cell now. This summary shows that all 18 numeric parameters have consistent counts with no missing values, each roughly centered around 0.5 with similar spread, indicating normalized features. Noticing these statistics helps confirm data quality before modeling and highlights that feature scales are uniform, so no immediate scaling is needed. This step connects to the lesson's intent by ensuring we don't overlook data issues that could mislead crash prediction. Spot one feature with the largest range. Why could this matter before modeling? Let us explore relationships between the first several features and the outcome. We use Seaborn's pair plot to visualize pairwise scatter plots for the first 4 features. Each point is colored by the simulation outcome. Patterns or grouping by color can suggest which features separate crashed from non-crashed runs. Running the cell now. This pair plot visualizes relationships among the first 4 features, colored by crash outcome. Notice how points cluster differently for crashes 1 and no crashes 0, revealing potential feature patterns that might help predict failures. This highlights the importance of exploring feature distributions and their connection to the target before modeling. Practice: do you spot any features that clearly separate the two classes? Let us check for linear correlation between the numeric features. We create a correlation matrix of all data columns. We set the figure size to control the dimensions of the plot. We draw a heat map of the correlation matrix using a color scheme centered at 0 to show relationships. We add a title to describe what the heat map represents. We display the plot on the screen. Running the cell now. This heat map visualizes the correlations between all numeric features, highlighting which parameters move together or oppositely. Notice clusters of strong positive or negative correlations, which suggest some features may be redundant or related. Identifying these relationships helps us avoid treating every feature as equally informative when predicting simulation crashes. Why might collinear features cause trouble in some models? Many models work best when features have similar scales. Let us standardize all features. We create a standard scaler to convert features to 0 mean and unit variance. We create an instance of standard scaler for scaling features. We select all columns except the outcome column as features. We fit the scaler and transform the data, learn and scale. We show the scaled values of the first row, which should be numbers around 0. Running the cell now. This output shows the first simulation run's features after standard scaling, where each parameter is transformed to have a mean of 0 and a standard deviation of 1. Notice the wide range of positive and negative values, reflecting how each original feature compares to the overall dataset distribution. This step is crucial to ensure all 18 parameters contribute fairly to the model, preventing bias toward features with larger original scales. Practice: why is scaling helpful before PCA or model fitting? Let us use PCA to compress all features into 2D and see if crashes and non-crashes cluster. We create a PCA model to find the two most informative axes. We run PCA on the scaled features and store the 2D projections. We scatterplot both PCs, coloring by the outcome variable. We label the x-axis as the first principal component. We label the y-axis as the second principal component. We add a title to the plot to describe what it shows. We display the plot. Running the cell now. This scatter plot shows the two main principal components summarizing the 18 numeric features of each simulation. Notice how the crash outcomes, colored differently, are somewhat mixed, highlighting that crashes aren't clearly separable by these top components alone. This visualization emphasizes why predicting crashes requires looking beyond simple linear feature combinations. If there is no clear separation, what does that mean for the difficulty of the problem? Now let us split the data into training and testing parts for fair model evaluation. We pull feature columns and the target outcome as separate variables. Make sure outcome is an integer for scikit-learn. We use train_test_split, holding out 25% for testing, and stratify to preserve class ratios. Setting random_state to 42 again ensures results are reproducible. We print out the number of samples in each dataset. Running the cell now. This output confirms that the dataset was split into training and testing sets with 405 and 135 samples, respectively, maintaining the original class distribution due to stratification. Notice the total matches the original dataset size, 540, ensuring no data is lost. This split lays the foundation for building and evaluating models while addressing class imbalance, a key concern in predicting simulation crashes. Why is it important to split the data before training a model? Let us train a quick baseline classifier and print key metrics. We create a random forest classifier with 100 trees and use balanced class weights to handle imbalanced classes. We train the random forest model on the training data to learn the relationship between features and labels. We use the trained model to predict the labels for the test dataset. We print a detailed classification report showing metrics like accuracy, precision, recall, and F1 score for each class. Running the cell now. This classification report reveals a glaring class imbalance impact. The model perfectly detects crashes, Class 1, with high recall and F1 score, but completely fails to identify non-crashes, Class 0, scoring 0 in precision and recall. This highlights the challenge of imbalanced datasets in climate simulation predictions, emphasizing the need to adjust strategies beyond simply balancing classes in the model. Notice how the accuracy seems high, 0.91, due to the dominant crash class, but other metrics expose the failure to recognize non-crashing runs accurately. Practice: which metric would you choose for this kind of rare event classification problem? Let us visualize how many conditions the model got right or wrong. Show a comment indicating the confusion matrix will be displayed. Calculate the confusion matrix using true and predicted test labels. Create a heat map of the confusion matrix with annotations and a blue color scheme. Label the x-axis as predicted to represent predicted classes. Label the y-axis as actuals to represent true classes. Add a titled confusion matrix to the heat map for clarity. Display the heat map plot. Running the cell now. This confusion matrix summarizes model performance on predicting simulation crashes, showing counts of true versus predicted labels. Notice how many crashes, ones, are correctly identified versus missed, which reveals if class imbalance or prediction errors need addressing. This helps us evaluate whether the model effectively distinguishes crashes to save computing resources as intended. What would high false negatives tell you about model safety in practice? We will look at the area under the ROC curve, which works well for imbalanced problems. We obtain probability scores for each test point from the model. Compute the ROC-AUC using scikit-learn scorer. This scalar tells us how well the model ranks positive vs negative class examples. Print out the ROC-AUC value. Running the cell now. This ROC-AUC score of about 0.92 shows the model is very effective at distinguishing between crash and no-crash simulations. Since the outcome classes are imbalanced, this metric is crucial. It summarizes performance across all classification thresholds rather than just accuracy. This high AUC suggests the model is strong at predicting crashes, helping save computation time and energy by identifying risky simulations early. Why might accuracy be a misleading metric for imbalanced data? Now let us see which features the model thinks are most important. Create a pandas series from the model's feature importances, using the feature column names as the index, then sort in descending order. Select the top 10 features with the highest importance and plot them as a bar chart with teal color. Set the y-axis label to importance to indicate the feature importance scores. Set the plot title to Top 10 Feature Importances, RF, for context. Display the plot to visualize the feature importance bar chart. Running the cell now. This bar chart highlights the top 10 most important features from the random forest model used to predict simulation crashes. Notice that a few features have significantly higher importance scores, indicating they contribute most to the model's decisions. Understanding which parameters influence crashes helps focus feature engineering and avoid treating all inputs as equally impactful. What is one way you could use this information to simplify or improve your model? Let us try using only the 5 most important features. Try using only the top 5 features for the model. Select the names of the top 5 features from the Feature Importance Index. Create a training set with only these top 5 features. Create a test set with only these top 5 features. Initialize a balanced random forest classifier with 100 trees and a fixed random seed. Train the random forest model on the reduced training set. Use the trained model to predict the labels for the reduced test set. Calculate and print the ROC-AUC score using the predicted probabilities from the top 5 features model. Running the cell now. This output shows the model's AUC score when trained using only the top 5 most important features, achieving a strong 0.93 AUC. Notice how focusing on just the key features can still capture most of the predictive signal for crashes, highlighting the importance of feature selection rather than using all parameters equally. This step helps prevent overfitting and reduces complexity, addressing a common beginner mistake. Did the AUC drop a lot or stay close? What does this tell you about feature selection? Let us look at a real example where the model might get confused. Comment indicating we are examining a single random test sample to investigate an edge case. Select a random index from the test feature set with a fixed random seed for reproducibility. Print a statement indicating that the feature values for the chosen test sample will be shown. Display the feature values for the selected random test sample in a readable format. Print the true label, actual outcome, for the selected test sample. Print the prediction made by the model for the selected test sample. Running the cell now. Here, we examine a single test simulation's feature values and compare the true outcome, no crash, to the model's prediction, crash. Notice how the model misclassifies this case, highlighting the challenge of borderline or complex parameter interactions in predicting crashes. This underscores the lesson's emphasis on carefully interpreting model errors to better understand feature importance and class imbalance impacts. Can you guess why the model might miss unusual cases, even if overall accuracy is high? Let us export test predictions for further offline review. Save model output for later analysis. We make a copy of all test simulation features. Add the actual outcome for each simulation to the data frame. Store the predicted crash probability. Save this dataset as a CSV file named the crash_predictions.csv for later. Print confirmation of the saved file. Running the cell now. The code saves the test features, true crash outcomes, and predicted crash probabilities into a CSV file for further analysis. Notice that this step preserves all important data needed to evaluate model performance and investigate errors later, which is crucial when dealing with imbalanced crash data. This file supports careful review beyond immediate metrics, aligning with the lesson's emphasis on thorough model validation. Let us open this predictions file so you can explore the outputs in a spreadsheet or Excel. Practice: what kinds of additional analysis could you perform outside Python if you have this CSV? Now we will handle class imbalance by giving more weight to rare events. Explain: we are adjusting for extreme class imbalance by applying sample weights during training. Create an array of sample weights giving a higher weight to the minority class, label 0. Initialize a random forest classifier without using built-in class weighting. Fit the model to the training data using the specified sample weights. Make predictions on the test set using the trained model. Output the recall metric for the minority class to evaluate how well rare events are detected. Running the cell now. This output shows a recall of 0.0 for the minority class, meaning the model failed to correctly identify any non-crash simulations despite applying sample weights to counter class imbalance. It highlights that simply weighting samples doesn't guarantee better detection of all classes, emphasizing the need to carefully validate model performance on each outcome. This reinforces the lesson's intent to handle imbalance thoughtfully rather than assuming equal feature impact or that weighting alone solves all issues. Does boosting the rare class weight always improve minority recall? Why or why not? Subscribe to our channel for more Python data tutorials, and comment below with your questions, Let us see what happens if we accidentally add non-numeric data. Explain that this is an error demonstration by adding a problematic string column. Create a copy of the original data frame to avoid altering it. Add a new column filled with a string. Many models can't handle non-numeric data. Start a try block to attempt fitting the model and catch potential errors. Try fitting a random forest classifier using the original features plus the new string column. Catch any exceptions that occur during fitting. Print the caught error to understand what went wrong during model fitting. Running the cell now. Here, the code intentionally adds a non-numeric dummy column to the features, causing the model to fail. Notice the error could not convert string to float, which highlights that all feature columns must be numeric for the random forest classifier. This reinforces the lesson to carefully check data types before training a model. Why is it important to check your data frame column types before fitting models? Now let us show what happens if a feature column is missing from your data. This line is a comment explaining that we want to catch a key error which may arise if a feature is missing. We start a try block to attempt running code that may raise an error. We try fitting a random forest model on the training data after dropping the first feature in the top 5 list from x_train. If any exception occurs during fitting, we catch it and assign it to variable e. We print a message indicating that an error was caught, showing the error details. Running the cell now. Tip: always double-check your feature names before feeding data to training or prediction functions. Best practices and common patterns. Always split trained test before touching the full data. Normalize or scale numeric features for consistent distance-based modeling. Investigate class imbalance and use suitable scoring metrics. Cross-check that all feature columns are numeric and contain no missing values. Use feature importance or model interpretation to guide improvements. Save predictions and models for audits and reproducibility. Running the cell now. Here is a minimal example from start to finish. Set the seed for reproducibility. Load the full dataset from OpenML. Copy the dataset into a new data frame to avoid modifying the original. Separate the data frame into features x and the target variable y, converting y to integers. Split the data into training and testing sets, preserving the class distribution with stratification. Create a random forest classifier with balanced class weights and a fixed random state. Train the random forest on the training data. Calculate and print the ROC-AUC score using predicted probabilities on the test set. Summarize the entire process from data preparation to model evaluation in a single cell. Running the cell now. The output shows a high AUC of about 0.92, indicating the random forest model performs well on the held-out test set. This confirms that splitting the data before modeling and using class balance weights helped create a robust, fair classifier. Notice how this quick pipeline respects best practices like stratified splitting and class imbalance handling, which are critical for reliable evaluation. Try timing this end-to-end cell and see if you could replicate it with your own datasets. ***, give this video a like and subscribe if you want more lessons like this. ***. Recap and next steps. You have learned to access, explore, and model real-world scientific data. You saw the importance of class imbalance and validation for rare event prediction. You learned to avoid common mistakes and export results for further use. Now you can apply these ideas to similar problems in simulation, engineering, or climate science. Keep practicing and experiment with different models, weights, or features to see how your results change. Running the cell now.